Yesterday I was talking about these transpositions. I guess close it, it's a bit noisy here, the conference. Well, you're just moving wires around. You have the horizontal, the vertical, and the transpose. And then you can also take the conjugate of the entries, so you get a total of 8 things you can do. And you can represent each of these well, first of all, I call these transformations, I call them transpositions. So that's a blend of the word conjugation and transposition. And conjupositions is better than the alternative, which was transugation. So I decided to stick with conjuposition. Here. Okay. So these are the 8 transformations that you have. And this is the full group of conjupositions that you can act on the hypermatrices with. And then there's a bunch of subgroups that are interesting for various reasons. So the subgroup consisting of I, H, so that's the horizontal adjoint, the vertical adjoint, and the transpose. That set turned out to be, I haven't done this yet, but you'll see how these are basis independent when you start to use them to look at Hilbert objects. Okay. And this basis independent set is behind the presentation of quantum theory that I'm giving you here. There's another subgroup which I'm calling the side group for reasons I'll explain in a little while. And this is behind the presentation of quantum theory in Kircher and Kissinger's book. And it gives you basis-dependent transformations, so it depends what orthonormal basis you use. But you can use it, but it's a possible alternative. Both of these subgroups have conjugation in them, and you need conjugation really to do quantum theory. You can't sort of get real numbers from complex numbers unless you have conjugation. So that's essential. And then 2 more subgroups. So these are the non-conjugating elements. So since it doesn't have conjugation, you can't use it to present quantum theory. This group is interesting because when you don't have conjugation, you can perform the corresponding transformations on the objects that you consider just by attaching wires. So by attaching wires, you saw that already, actually, a few slides earlier. By attaching wires, you can do these non-conjugating transformations, but you can't get the conjugating transformations simply by attaching wires. Then there's another subgroup, the conjugating group, which consists of all the conjugating transformations. Which also is overkill for doing quantum theory, but it is an interesting group, and I'll use it to set up this theory of mirrors. So using this subset, so you can have mirrors corresponding to H and V, and also mirrors corresponding to I and H bar and T bar, so H bar and V bar. And also mirrors corresponding to these elements. You'll see that later. Okay. So here's an important point. If you take a bunch of hypermatrices and you join them together in whatever way you want, like this, and then you perform one element of the conjugation group on the whole thing, then that can be implemented just by performing it sort of locally in each box and rearranging the diagram. So basically, the whole diagram preserves its structural form when you do this conjuposition. And that's not difficult to prove, but it's a very useful property and really is important. Any questions? All very clear? Okay, so orthonormal bases, so these play a big role in quantum theory, and I'm going to use them to expand Hilbert objects that I talked about last time using hypermatrices. So the normal sort of notation you have is like this. So you have some basis, and remember we had these 4 different Hilbert spaces that were interesting to us. So these would be the corresponding orthonormal basis set, and you have these orthonormality conditions. And I'll give you the diagrammatic form for those same equations, same objects. So diagrammatically, we'll represent a orthonormal basis by a box like this with nothing inside it. And then the orthonormality conditions are written like this. Sometimes we want to consider more than one basis, and then we can use different shades of grey to indicate that. You look like you have a question.
No, I'm just trying to remember what all these different wires.
Oh yeah, so this is this one tells you which Hilbert space you're in. Okay, and this is an out. So this is a outgoing one. This is a label wire. So A takes values from 1 to.
Right, this labels your basis state.
Labels your basis, yeah. Basis states, yeah. And so, if you have a certain basis and you come around, and this is really, you can think of this as A and A prime because they're in different places. So then you get, this is equivalent to the delta function. Is that clear? Okay. Then you can use this to do decompositions of the identity. So you're familiar with this decomposition of the identity, or this one, and you can, but you can write those down diagrammatically, and they take that kind of form. Okay. And also, there's these decompositions of the identity. So again, you have like that, so this is just the identity, and you can represent this by a cap that looks like that, and the same here, you can represent it by a cup.
Like one is identity on the Hilbert space, the other is more like identity on the operator space, if I'm thinking about quantum mechanics.
Yeah, I think that's right, yeah. I mean, whatever you put in here, if you put some Hilbert object here and act on it, the same thing will come at the top because you're just putting this wire on it. Whereas here, yeah, this is an identity operator. Yeah.
Previously, we're already writing we have the I box and the R box.
Yeah.
Right? Would this be the same?
Yeah. Not exactly the same. There's some scaling, and that's important, and I will come to it. Yeah. You can see in normal notation in standard quantum theory, this is the same as the I box, because the I box in normal quantum theory is just tracing.
Yeah.
And that's just the identity.
Yeah.
But this is not the maximally mixed state in standard quantum theory. But actually, you really have gauge parameters. The only thing that's important is that this acting on this, that the ignore box is acting on it should give you 1. And so you have to get the right scaling. And I'll come to that. Okay. These identity relations are independent of the choice of basis. there's actually there's 10 different ways to combine these basis elements together at the label wires. So here, this is 4 of them. There's another 6 ways which are in the book, which I think I deleted the slide, for that to save time. But those also play a role in this framework. Okay, so now what I want to do is think about normal conjupositions of Hilbert objects. So what we can do is we can take some Hilbert object and expand it using a bases for each of the systems. So write it like that. And then already here we've got the flipped version, the horizontally flipped version, where we have B bar. And there's something that's not quite pleasing about having the B bar to indicate the complex conjugate. It sort of breaks the symmetry of this flipping. So instead, I invented that notation. So this and this are the complex conjugates of each other. Okay. The other thing here is there's this black dot, which we had before, didn't we? Okay, so that you've seen already. That's useful to follow the various conjupositions.
Right. So another way to get the black dot from left to right was to do to
bend the wires
around.
Yeah,
but that's not what's happening here.
Well, here we've done more than bend the wires because we've also taken the conjugate. Yeah.
I think it is happening, right? Bending the K to the left,
Yeah.
and the A and B to the other side,
Okay, so you do that and
and the conjugation.
Yeah. So you can, imagine if you didn't have this conjugation, and that is one of the conjupositions I'm interested in, then you could represent this transformation just by bending wires, and that's in the book. You've also got to make sure these wires get bent appropriately because they have to. This has the bubble on the left, and over there it's got the bubble on the right. So you have to twist that. So all that can be done for the non-conjugating conjupositions, but it can't be done for the conjugating ones. So let me just show you. So here's 4 of them. Okay, and then here's another 4. So I'll just go through them. So to get from here to here, we want to call this the normal horizontal adjoint. Normal because we're using orthonormal bases. Horizontal because we flip from this side to this side, so horizontal flip. And adjoint because we take the complex conjugate. Yes?
What is the black square on the operator Hilbert object on the left?
Why is it here?
Yeah.
So that's the convention I'm setting up. So I'm saying when you take so in some sense the natural thing in quantum theory is the adjoint. Okay. So I want that to be the sort of thing that works most naturally. So that when I flip it, flip it horizontally. I just get the flipped object. This is kind of the natural thing to do.
And should the bubbles,
The bubbles, yeah.
should they be on the other
Oh,
side?
there's a mistake. Yeah. Gosh, thank you.
Okay.
Wow. Okay, I did not see that. Yeah, they should definitely be on the other side. That's yeah, that should never happen. That's
Okay.
yeah, but that's wrong in the book as well because all of these pictures were taken out of the book. Yeah. Thank you.
Okay.
Good. Yeah. Yeah. So of course it has to be type matched across the equation. Okay. So we can also go from here to here. What we've done now is flip this diagram vertically, and that corresponds. And we've also taken the adjoint. Sorry, we've taken the adjoint. So we've taken the complex conjugate of these elements. And this is also a very natural thing in quantum theory. And so this is the normal vertical adjoint.
So why does this not go from B to A?
Which one, sorry?
Um,
Have you found another
bottom left diagram has A as input.
Yeah, and that is another mistake. Gosh. Okay, this is all going to be much better on the picture, which is the next slide. Yeah. Well, I must have been very sleepy the day I did these pictures. Yeah, that's entirely wrong. Okay, thank you. And then, modulo the two errors that have been found, here's the case where you have the other conjugation on the elements. So let me show you all of this in the Hilbert cube. Okay. Okay, and this time, yeah, this time I've got everything right here. That mistake is still there. Wow. Yeah, that bubble is on the wrong side in each of those. I don't know how I didn't notice that. Okay, but at least the names of the things are correct. Top and bottom. Okay, so you can see to go from here to here, you take the normal horizontal adjoint, and so on. And I've drawn. There's also transformations that go along the diagonals. There's the diagonals in each face, and there's the interior diagonals of the cube. So from every element, there should be 8 conjugations to get you to each of the other. Well, it includes the identity, and then the other 7 ones. Okay, is that clear?
Yeah, and the little square dot on the
Yeah.
Hilbert object, it moves to the side if you take just the complex conjugate.
Yeah, that's right. Yeah. So I had to set up a convention.
Yeah.
And so this front face here is the natural place we want to be. This is our happy space, so to speak. And then at the back, we have another thing like that, where all the elements are conjugated. You could also live in that space quite happily. It has all the same properties as the front. I call the thing at the back the shadow, a Hilbert square. The one at the front is the Hilbert square that we work with. But you could transform everything into the back. That would just be like taking complex conjugates of all the numbers in quantum theory, and you'd get the same results. Okay. There's also these sides, like this side here, and that's the place where Kircher and Kissinger work, interestingly. So they work in this side. The disadvantage of that is that you have basis-dependent transformations between these objects, because some of these conjugations are basis dependent. But there are certain advantages they talk about, and if you look at their book, you'll find they explain why they prefer to use this side than this front square. Okay.
I think I'm a bit confused about what it makes to only work with the front, only work with the side, only work with the back.
So when I'm going to form the Krauss, I'm going to form this Krauss decomposition. Okay, I can take these two things and join them together. But I might be interested in some kind of something like a time reverse of that, where I flip and I use this thing at the top instead, and I bring those two together. There's another place we might be interested in unitary transformation. So all of these B's become U's, and these are now unitaries. And then I can take the scalar products of this and this, and if they're unitaries, that should be equal to just the identity wire. So there's a lot of play that happens in here, and you can play with the whole space, but it's this front square that sort of is important, really, for setting up quantum theory. The whole space, I think, is interesting. Maybe I'll have some chance to talk about more of that, but it's the front square that's useful.
Right, as you said, the front one is the one we usually work with.
Yeah, exactly. Yeah.
And then the side one, what did it mean like when I write the cross operators? Somehow I
Yeah. So unfortunately, I deleted the slide I had on that, and it would take me sort of out time. But I can show it to you in the book. There's a bit where I talk about what Kircher and Kissinger do, and you can work. You can take a Krauss. You can set up your Krauss operators with this thing and this thing if you want, and it's all consistent, and you get the same answers. It's in the book. I just thought I'd save time by underestimating my audience but your question is good.
Listen, is there a simple way to explain what happens in the, let's say, algebraic notation when you have a, let's say, h bar or h, or
I'm not sure what you mean by the algebraic notation.
well, if you use like cat-bra notation?
Oh, there may be. One of the problems is that if you're using Kep-Bra notation, you have this kind of sort of wrong twist. You can't naturally represent these things.
Exactly, yeah.
But I think if you just restricted yourself to things that had only apples, I think you could do that. And I know that that's sort of where kind of the natural intuition lies.
Okay.
But I haven't done it because I wanted to develop a different intuition. Okay, so this is the front square thing. I'm just calling the Hilbert square, and so the transformations there are you have the normal horizontal adjoint to go across, the normal vertical adjoint to go up and down, and then the normal transpose to go between those. Okay, and then this is the side Hilbert square. You have one on the left, this is the one I've drawn, you also get one on the right, and that's the thing that's used by Kircher and Kissinger. It took me a while, because I was reading their book and I was puzzled as to why they had differences between what they were doing, and after a while I understood that they were using a different part of the Hilbert cube. There are, incidentally, other squares of objects in here you can find, like you could consider the square consisting of these two at the front top and those two at the bottom back. That's also a square you can consider, and so on. Okay. So remember, we have that property that if you put together a bunch of hypermatrices and perform one of the conjupositions, the thing transforms in a way that preserves its structural form. This is also true when you wire together a bunch of Hilbert objects, possibly also including some hypermatrices, and then you can perform one of the conjupositions. So here I've shown the transpose, but this works for any of them, and the thing will preserve its structural form when you do that. Okay, well, one example of a Hilbert object, this has now got, if you write this down, you could write this down in terms of left and right Hilbert objects. So these operator tensors are themselves Hilbert objects. So one example would be a circuit like this, a circuit built out of operator tensors. And we can now ask what is the interpretation of these conjupositions? Well, if you take the horizontal, the normal horizontal adjoint, then you get this, and because it's the adjoint, you get P bar. So you really want P to be equal to P bar because you want this to be a probability, and that is guaranteed if all the operator tensors are Hermitian. Okay. What about the transpose? So in that case, you rotate the circuit, and you get that, and the circuit retains its form, and you get the same probability. And if you remember how I defined time symmetry, I said I want it to be the case that you can map between circuits in such a way that you get the same probability. So you can find a way to invert. So this looks like it's a great candidate for the time reverse map.
Even though the conjugate transpose would be often what we would think of as a time reverse, right?
Yeah, there's if you have emission objects, then if your operator tensors are emission, then these things amount to the same thing. Yeah. So you could use any of those as long as your operators are emission. Yeah. The advantage of the transpose is that you can just do it by attaching wires. But if there's a conjugate involved, you have to. Yeah. Was there another question?
Can I see the previous slide?
Yeah.
I was H bar, okay.
Yeah. Okay. Here I've just picked out two of the conjupositions. In the book, there's a discussion of the other conjupositions and how they fit into the story. So addressing this question, for example, and the others. Yeah. So it looks like this is great because it does what we wanted. Okay, but you can perhaps tell from my intonation that it's wrong. And the reason for that is that the normal transpose does not map between the ignore operators. And it would have to, otherwise it wouldn't make sense. So let's look at that. So the ignore operators play this central role. We want them to have the property that they give 1 when you put them together. So we can write them down like this. And then because the 1, this identity operator here, being acted upon by this, gives you n, the dimension of the Hilbert space. If you just take the trace of 1 times 1, you get n. Then we need to make it so that these normalization parameters multiply to give 1 over n. Is that clear? Okay. And so now it's actually more convenient for what we do subsequently to think of these ignore operators in terms of these basis elements and introduce these gamma and gamma bar parameters that now where the gamma squared is equal to the alpha I had before. Okay. Is that clear? And now if you look at this, you can see that if I take the transpose, it's going to fail, because if I take the transpose of both sides of this thing will turn upside down. These numbers will stay as they are, but they so you'll get this, except that you'll have the wrong numbers in here. Rather than having superscript A, you'll have the subscript A. So if you take the transpose of this, you get the wrong thing.
Okay.
You can also do that by attaching wires. Okay, if you take the transpose of this, I haven't explained this notation, but anyway, this is a way of taking the transpose by attaching wires. It turns this thing in the middle upside down, but leaves these gammas where they are, and that is equal to the corresponding ignore operator multiplied by some different constants. Now you can make those equal to 1 by choosing those to be, and that would be one solution, just to fix that. But I think that you end up missing a lot of really interesting math if you fix those. So I think it's better to keep them variable and look at it like that. Okay. Anyway, so you can see that it doesn't quite get the normal transpose doesn't quite work because it gets these gauge factors wrong. But you can imagine that this would easily be fixed by having some kind of rescaled transpose. Okay, but how do we do that properly? Well, to do that, I'm going to define something called the orthophysical bases. So instead of using orthonormal bases, we use these new bases called orthophysical, which are rescaled. And then that naturally leads to the right transformation there. Okay.
How should I think about like if the box with one open side, if that's already also normal, then how could lambda not to be one?
So which box are we talking about?
The second one, the second figure.
This here?
Yeah, if those already represent some kind of Hilbert object that is also normal basis,
Yeah.
then how could lambda a not equals to one such that you have the decomposition of the ignore operator?
How could this not be?
No, how could the gamma
Yeah.
not be one? I guess the problem appears when gamma is not equals to one, right?
Yeah, well, and gamma can't be equal to 1 because gamma superscript times gamma, well, because we have this constraint. So they can't both be equal to 1. You can't have gamma superscript A times gamma subscript A equal to 1 because they have to be equal to 1 over n.
I see.
Yeah. So that's not a choice we can make. We could choose them both to be equal, in which case they'd both be equal to whatever, 1 over the fourth root of n.
I see. So this is somehow like when people choose the coefficients for Fourier transformation, you can put all the coefficients on one of the Fourier transformation, but not the inverse. But
That might be. I'm not so familiar with that example, but that may be a way to.
yeah, but I see the point.
Okay. 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 So we're going to define a different basis, and then this will do what we want. Okay. And this is going to lead to a different notion of conjuposition, which I call natural conjupositions. So I can't pronounce the word I've invented now. Natural conjupositions. Okay, and so you've got normal conjupositions, and those don't work. So now we go to a new notion, the natural conjupositions, and those will work. Okay. So we define Hilbert objects now. Instead of expanding with respect to the orthonormal basis, we expand with respect to this new basis I'm going to define. And then we can get these natural conjupositions, and we'll find that the natural transpose does transform between the ignore preparation and the ignore result. Okay, so this will all work. So an orthophysical basis is defined like this. We take the original basis, the orthonormal basis, and we put the gamma, the corresponding gamma, in front. Okay, for each of these. Okay, and there's a little triangle now instead of a square.
Do we lose the basis independent feature we had before, or?
No, we don't. That retains. Yeah.
Okay.
To make this work well, we need to impose that gamma A superscript times gamma A subscript is a real number. And then the normalization said it would have to be equal to that. If we don't impose that condition, various things go wrong. Like the composition, the fact that you get the same structural form after transformations doesn't work. Also, there's orthogonality. There's things that are like the orthogonality conditions are not as nice. Okay, so we impose this. I call that the orthophysical gauge normalization condition, and I really should have thought of a better name. And then we get these conditions, so they're different from the ones I had before because you have this factor in front, which is natural because you have these gammas coming from.
So just as an example in sort of traditional language, would it be that if I if I insist on describing my cats with, I don't know, by an orthonormal basis, then my bras would be still orthogonal, but just all the vectors would be subnormalized.
Oh yeah, so you're saying you could, which ones are, well, I can't actually remember now which, I think these were Kets and those were Bras.
I guess.
Although over here there's a,
Yeah, I realize that there's
yeah,
a difference between cats or graphs versus
yeah,
vectors in the dual space.
yeah. I mean, there's probably a way of, I'm sure there must be a way of doing what you're saying to make it work. Yeah, if you want to think in terms of Bras and Kets. So, I mean, that's sort of, I don't know, that's like going to the antique shop and trying to understand how a sort of, you know, an iPhone works or something. But yeah, you can do that if you want to.
Sometimes it can help.
Okay, and you can also join these. This time I've actually given you all 10 ways of joining these objects. We're not going to really focus on the 6 at the bottom, but the 4 at the top are the ones that correspond to the identity decompositions I gave you earlier. But they're not quite identity decompositions. They end up being proportional to identity decompositions, and they carry, you know, because you have these gammas in here, and these little tildes kind of remind you of that fact. Okay. So it's easy to work out what the normalization would be, if you want.
Wait, so number 1, for example, is it the identity operator on this Hilbert space, or is it?
Yeah, it's the identity times. Well, you'd have a gamma superscript here and a gamma subscript here. So this tilde means that you have a factor of those gammas multiplied together.
Which is 1 over.
Which is exactly 1 over square root of n. Yeah.
Square root of n times that.
Yeah, exactly. Yeah.
And the W tilde, you have a conjugate somewhere.
Which one?
The third case.
Yeah, here you've got a mixture of different ones. These are very interesting as well, but I just don't have time to go into.
And there you're twisting the bubbles.
Yeah. Yeah. So these, you know, remember I said you could apply all these conjupositions by attaching wires.
Yeah.
And for some of those conjupositions, you need to use these twisted ones. Yeah. So the W stands for twist because there's a W in twist, and I've already used T so much I don't want to use T again.
I see.
Yeah.
Okay, so the right-hand column, number 4, am I right that would be the properly normalized Bell state? There's a 1 over square root n in the pure picture. Right?
Yeah, it is the Bell state. I'm sort of worried about the properly normalized statement.
Or well,
Yeah.
in
It is a Bell state,
what
yeah.
would normally what sort of
Yeah,
in the forward time picture would be called the normalized Bell state.
yeah, I think that,
Square root n of sum over
yeah.
vector times vector.
If you've got, times there'll be some phase potentially because you've got, but yeah, I think that, no, hold on. No, because this has got both gamma subscripts, and so we haven't got a, well, maybe, yeah, it will have some appropriate normalization property. It's just, in the normal picture, you always, you impose your normalization at the level of preparations, and then you separately, whereas here you have a combined normalization. And I think if you have that combined normalization picture, it will do the kind of thing you're asking for, I think. Yeah, I'm pretty sure that's the case. Okay. Okay, so now I want to go through the same exercise with all the same typos, apparently, as before. So you have these things that now instead of, it's going to be a lot of work to put all that right, I hadn't noticed. Anyway, you have, you can do the natural horizontal adjoint from here to here, and so on, all the other adjoints, all the other conjupositions. And you have, okay, this is the notation. So now I'm notating these natural conjupositions when they act on Hilbert objects using the under tilde. or \u tilde. One thing to note is that the natural horizontal adjoint is the same as the normal horizontal adjoint. If I go back, you can see that here, if you want to, here you basically have a gamma with a B superscript, and here you have a gamma with an A subscript. Then over here you have the complex conjugate of those same factors, and the horizontal adjoint takes the complex conjugate. And so the natural horizontal adjoint is the same as the normal horizontal adjoint. That is not true for the other non-trivial conjugate positions. It is true, of course, for the identity. Okay. And here's the cube with most of the typos fixed. And it's the same story as before, except that really this is the place I want to live. This is actually the happy place because this is all natural. Whereas previously we were using these normal objects which weren't quite right.
And this is natural because we are in the time symmetry.
Yeah, in the time symmetric. Now, you could also use it in the time forward framework. You wouldn't have quite the same motivation, but you could, of course, also use this. Yeah, I think you wouldn't have quite the same motivation, but there's no reason not to use it. Okay, and this also, you have the property that the compositional structure is preserved under these natural contrapositions. In this case, it's essential that you have this assumption that gamma A superscript times gamma A subscript is real. Otherwise, it fails. It took me a while to understand that. And now, the ignore operators transform into one another, because the ignore operator is just this, because you've got these gammas which give you the right normalization, and this, those things, if you hit this with this, you just get 1 because of the normalization. And you can see, if you take this thing, it's got if you want to perform the natural transpose, you just rotate it because the compositional structure is preserved, and you get that. Okay. And so.
Sorry, why do we? I think I lost track of why do we care about why do we want this natural transpose such that you can transform the ignore? Ignore. Yeah.
So we're looking for we want to have a time symmetric formulation. Actually, maybe I'll show you the next page. And so we want it to be the case that we have a way of transforming. We want to have an operation, something we can do to our operators that takes the time reverse. Because our definition, I don't know if you remember, I think it was the very first lecture, our definition of the time reverse is that you can take any circuit, replace its object in it with its time reverse, and get the same probability.
Okay, and now we are trying to find explicitly what's this transfer.
Exactly, yeah, exactly what it is, yeah.
Okay.
And for that time reverse to work, it would have to transform ignores to ignores. That's just that's a basic requirement. But what about more generally? And so if we perform the natural conjuposition on this, by the way, I've now got these side wires. I'm not going to explain how you do the transposition on those as well, but it's in the book. So if you can just ignore those for the moment if you want. So there is a way now of defining a natural transpose of this, which takes you to that. Okay, you can see it rotates the thing upside down. And yeah, and so it looks like this is a good candidate for the time reverse, and then you can check that it has the right properties. So the main thing is it's got to map between allowed operators. And the allowed operators are the physical operators. And so it's got to preserve positivity, which it does, obviously. And it's also got to preserve double causality. And you can show that what it does is it transforms the forward causality condition into the backwards causality condition and vice versa. So it does exactly preserve double causality because those two conditions just get swapped. Yeah, so this is the proofs of this are in the book, but it's I think pretty clear by now that this sort of thing will be true.
The reason the X and Y fonts are different?
I was asking.
X and Y are what, sorry? That's a typo again, thank you. They should be in, this is correct. I've made a mistake there, thank you.
And also going back to my question about the difference between transposing things and conjugate transposing.
Yeah.
So, like you said, like if we restrict to physical operations, their omission, then it doesn't really matter what we do mathematically. But I can now see a reason why you maybe want to think of the rotating thing.
Yeah.
Because you also have these wires from the side.
Mm-hmm. Yeah.
And because I'm usually used to just having
A wires on the bottom, top, and right.
bottom and the top. It doesn't, or even diagrammatically, it doesn't really matter whether I flip it vertically or rotate it. But here it seems really to matter for the diagrams whether.
Yeah, you're right. I hadn't thought about it like that. I mean, maybe that's just a happy coincidence for me because I think it's more natural to take just the transpose as your time reverse because you can implement that by attaching wires. So you can take this thing and attach a natural, here you can attach a natural cup, that's one with the tilde in it, here to bend that wire up, and a natural cap to bend that wire down. And then there also exist caps or side caps and cups for these X and Y wires. And you can do that just externally by attaching these wires, whereas to do something that involves conjugation, you have to get inside the expansion matrices. So there's something more appealing, I think, about the non-conjugating.
So the thing that I normally find not appealing about transposing things, and maybe it's different here and I missed something, but is that in the Cook and Kissinger approach, at least, these caps and cups, they are basis dependent, so the transpose is basis dependent.
Right, but that's not the case here, because they're using, and I think the words they use, like when they use the word transpose and so on, those words might mean different things than in my context, because they're using that side Hilbert square. And so they have these basis dependent objects, and so the caps and the cups also are basis dependent, whereas the caps and the cups on the front are not basis dependent, and so it's a different picture. Yeah.
Oh, is it because
they're just decompositions of the identity? Remember the thing, and that's independent of what basis you use.
I think like in some older Bob Cuckoo works, I've seen him also write in the book it's kind of simple. In the Kissinger Cuckoo, it's kind of simple, but you just draw the cups like that.
Yeah.
Any annotations, but sometimes you see these cups with like you said, a down arrow.
Yeah.
And that I guess that
might be what I'm doing here. Yeah, I think so, because I don't have the slide with their cups on.
Because that represents not an entangled state on two of the same systems, but rather an entangled state between a system and its dual.
Exactly. Yeah. So I don't have. I only have the natural ones, which have this funny normalization. But that aside, you can see that here the bubble is on the same side in each case. So you can't think of the bubble as naturally sliding down and over, which you can on these ones, which are basis independent.
The transpose, you're defining it in terms of 2 and not in terms of 4.
Yeah, that's right. Yeah, the transpose you used 2. Yeah. Okay. So I'm going to go on to talk about mirrors. So are there any questions at this point to get people on track? Is it all clear enough? I can also afterwards go through it if it's not clear. Okay. So it's fun, and I think it may even be mathematically deep potentially to introduce this mirror notation. Okay. So you have so here's the idea. You have a Hilbert object. It's attached by a label wire to a mirror, and that just means this. Okay. Which makes sense because all I'm doing is if I look in this mirror, I can see this image. Okay. So it's a sort of natural thing. But this definition works if you've got a label wire attached. What about if you have one of these system wires attached? Okay. Well, then you need to make sense of that. Well, you can think of it like this: if I reflect a basis element into a mirror, then it's equal to that. So, and this thing is just the identity, the cap, and then I can define that as being equal to that. Okay, so that's just natural. So that allows me to attach wire to mirrors. You can do the same in the other direction. And so now you can make sense of an expression like this. So this, you can write it down like this. And these kinds of expressions are typical in quantum theory. You often have this kind of thing. So it's useful notation. And of course the mirrors can reflect on either side. There's no reason to restrict yourself to one side. Okay. You don't have to have any wires attached to the mirror. If you just have an object and it's reflected, then you get that. Incidentally, I call this homogeneous operators when there's no summation. The reason for that is if this is just a preparation, so there's no systems going in the bottom, then this would correspond to a pure state in quantum theory, or a state which is subnormalized but still proportional to a pure state. And you remember on the double cone picture, I call those states homogeneous. So this is a way to extend the notion of homogeneous to these things in general. Okay. And there's no reason to make the mirror stretch all the way up and down. If you get very close to this mirror and you look in it, okay, then you can see this whole thing reflected. You might have to get very close. But if you look in here, you'll be able to see all of this reflected. And so this also has this meaning. And by the way, this mirror, what it's doing is taking the normal horizontal adjoint on the other side, and so complex numbers end up getting conjugated if they're reflected. Okay. You can also define mirrors with respect to the normal vertical adjoint, and that's just the natural definition. You say this, but then you also have to say what it means if you attach the wires to the mirror. And I don't want to spend too much time on this, but it's the same kind of basic principle as before. Okay. And so then, an expression like this just looks like that. Okay, so I've taken some expression and I've reflected it out. You know, when you have brackets in mathematics, you talk about multiplying the brackets out. An expression here, you can reflect it out, and it's just the same thing. It's just the same piece of mathematics.
If you think about the horizontal or the vertical mirror,
Yeah.
then it's kind of like I can think of it going from the pure formalism to the mixed formalism, or is that inaccurate?
I think that so the mirror that is horizontal, the one I had before. Yeah, that's right. Yeah. So if you so this is still sticking within pure, but there's no wires attached. There's no label wires attached. But this one here exactly enables that. So here is a Krauss decomposition of a completely positive map in standard language, but it has got a label over here.
Okay. So what I meant from pure to mixed, I guess I mean from
Ket
to Ket Bra, or like anyway from operate from Hilbert space to
Okay.
operates. But anyway, so my question was going to be for this one.
Yeah. What is it?
How can I think of it? Does it have a similar interpretation?
Yeah, I'm not sure. I think so. The reason I need this is because there are definitions that work with this mirror, like the standard definition of unitarity is where you have a unitary operator followed by the in my language the normal vertical adjoint, and you put it on top, and that can be written in mirror language. You'll see that later.
Right.
And then there's also a kind of unifying theorem for these mirrors, which I'll mention but won't discuss in detail. Yeah, so they kind of form a whole. Both mirrors seem to go together very nicely, as if they're there's a sort of deeper point, which I think there's. Maybe I'll make this point when I come to it, but there's a kind of this different ways of writing down the same equation using mirrors or using different mirrors. I'll come to it. Okay, so that's an example. You can also so here I defined my mirrors. Previously I defined them in terms of H bar and V bar. But you can also define in terms of I bar and T bar. And then you get mirrors that I guess they would be more natural in the Kircher way, Kircher-Kissinger kind of way of thinking. But they're interesting to set up. And I won't define them, but I represent these by smoke-filled mirrors, because it's smoke and mirrors. That's an expression in English. Is that an international expression? You know, you ask how a magician did a trick, and you say, well, he did it with smoke and mirrors. Mm-hmm. Okay, so this is a smoke-filled mirror, and what it does is it reflects using I bar. So the thing it forms is just taking the conjugate, and so this will be a definition like that. And these objects are natural in the Kircher-Kissinger way of formulating quantum theory. You could also try to set up mirrors with these non-conjugating elements, but it doesn't really seem to, it isn't much use, and so I didn't do it. It doesn't seem to buy you anything. Okay, so this is the mirror theorem, the normal mirror theorem. And it might be best if I show you an example, and then afterwards you can look at the words. So here's an example. Here's an equation. And this equation has the form that I have some expression reflected in a mirror, and on the other side I have another expression reflected in the same kind of mirror. And what I can do with the mirror theorem is I can apply any conjugaposition, the same conjugaposition to this, and I can also change the mirror to any kind of mirror. And that may entail dragging wires. So here's an example. That equation is equivalent to that equation. So I've both taken a conjugaposition on the bottom. You can see that the black dots inside the squares have moved. And I've also changed the mirror and dragged the wires as necessary. Okay. And so this theorem, it's interesting. It's something you can prove, and I think it's often there this theorem is often there in the background in quantum theory when we do calculations. So here's an example of a property that many of you will know about, which follows from the mirror theorem. It's this property. So if you take a maximally entangled state, remember this is a maximally entangled state, and you apply a unitary, and the unitary you get by conjugating.
Sorry.
What do you say, sorry?
So there's no tilde, so it's not normalized maximally entangled.
Yeah, that's right. This one, sorry. This is the one coming from the normal, which I didn't show you. So I didn't show you that. This is the one based on orthonormal basis elements.
Mm-hmm.
Yeah. So yeah, you have a maximally entangled state. You hit it with a unitary on one side, and the unitary you get by applying by conjugating all the elements, and that just gives you back the same maximally entangled state. And I think probably many of you have come across that property in some form or another. That property is equivalent to this defining property of unitaries using the mirror theorem. And you can almost see that. Here I can represent this by putting a mirror. This W means I need a smoky mirror. And so I can have a mirror here. And then I can manipulate that equation into this form, or I could have gone the other way.
So this mirror theorem, it holds not only in time symmetric theory, but also...
It holds in, just standard quantum theory, yeah. You can, this is not restricted to standard quantum theory.
Is there, like, if there are wires not connected to the mirror, does the mirror theorem also hold?
I mean, yes. I've not written down any examples like that, but I think you would often end up just with conjugation, like taking a. You could have. Well, one example would be where you have a scalar on and then you just end up getting the alpha times alpha bar. But you might also have wires, and then my claim is it does hold. Yeah, so I hope that's true.
Cool.
Yeah.
Because I was wondering what happens to the wire that is not connected. Like, does it also bend like this? I guess, or does it stay?
Oh, I see. Right.
It is not dragged with the mirror.
Yeah, it doesn't have to be dragged with the mirror.
Mm-hmm.
So so it wouldn't bend. Yeah, but I think it'd be worthwhile writing down some examples just to investigate that.
Cool.
Yeah. Okay. And of course, you can do all of this instead of using normal orthonormal bases to define your mirrors. You can instead define them using orthophysical bases. And these mirrors are more natural for me because I want to do the time symmetric quantum theory. So here, I've actually, this is a general Hilbert object. It could be something that's made out of left and right Hilbert objects, and I'm representing it in a more compact notation with a bit of flat surface available on each side to attach label wires to. In any case, the idea is the same. You define it so that it performs the corresponding transformation in the reflection, and then you, when you attach wires to the mirror, like system wires, you use these equations from before. So, for example, if I attach this thing, well, that reflects out to give me that, because I'm just reflecting the normal way. And that is equal to this. This is just by definition. And I represent that, I say that's what I get if I just attach a system wire to the mirror. Okay. So these mirrors, these natural mirrors with the curly bit here, are the same basic idea, but we're using the orthophysical basis to define them instead. Okay, and you can do the same thing. You can do the same thing for horizontal mirrors and vertical mirrors. I haven't set that up. And you also get a mirror theorem here. And this mirror theorem doesn't work quite as well. And this, I'm not going to explain this. There are these things called special caps and special cups, which you have to define them differently. They end up appearing when you apply the physical mirror theorem. That problem goes away in the second half of the book when we look at complex operations and operators and so on. I think the notation in that is more natural, but that's a okay. Okay, so physical significance of physical mirrors. So physical mirrors have the property that this is true. This is just by definition. This is the same equation I had earlier when I defined the mirrors. I should show you. See, remember, this is just the ignore operator. This too. Okay. And so you can give the physicality conditions for an operator tensor, in terms of these physical mirrors. So one condition is that that's true, and that guarantees positivity. Okay. This condition you could equally have given it with a normal mirror, because the horizontal adjoint is the same in both cases. And then over here, we have the forward and backward causality condition. So this thing here joins onto this mirror, gives you an ignore operator, and so this is forward causality. That's just the ignore operator on the input. Okay, is that clear?
Gives you an ignore operator.
So remember the forward causality condition is this. And if I want to do it for operators, I have to put hats on these things. But this I, these ignores are just given by that. And so we can see that's the same condition. Yeah. Okay. How are we doing? Then I kind of alluded to this earlier. You can use these mirrors to set up the unitarity conditions. So if you look at that, if you imagine reflecting this out, you have a unitary followed by the normal vertical adjoint of the same unitary. And if you reflect this out, you just get the wire going up. Okay, and that's a standard condition for unitarity. And then you can represent that the other condition for unitarity is the same thing where the boxes are joined in the other order. So these boxes are joined at the B wire, these ones at the A wire. Okay. Any questions on this? I can just draw it.
I'm trying to understand the difference between the top and the bottom.
Sorry, when you say you mean this one and this one?
Yes.
Yeah, okay. So this is the same thing you reflect out, but now because you've got a natural mirror, when you reflect out you have this a tilde circle in the middle.
Okay, so you're gonna have a proportional to identity on the bottom.
Yeah, that's right. Now, it turns out that constant actually can, if you assume at the right, let's say you put an A here as well, so A and A, then that constant actually goes away. But you're still doing a different adjoint. So you're still doing a different. This is the natural vertical adjoint, and this is the normal. So they are different expressions for that reason.
Mm-hmm.
So they are slightly different conditions. Okay. Any questions?
Can I use a normal meter in a natural unitary? And would that give me some proportionality condition?
Yeah, but then you also want to get the right adjoint, and V is not equal that. So yeah, you'd end up with lots of constants around. It wouldn't work very well. And really it turns out that it's the natural unitaries that are useful for us, because by the mirror theorem you can rotate these mirrors and you have these conditions instead. Okay. And those conditions here have the same meaning as this. And this is simply the double causality conditions for a homogeneous operator tensor. So that's and so in fact you can say that if you have a deterministic homogeneous operator which is physical, so it satisfies positivity, which means in this context twofold positivity, and it also satisfies both causality conditions, the forward and the backward, then in fact it's a unitary operator. It's a natural unitary operator. And you don't have that same simple statement for the normal unitary operators. Okay. Okay. I can keep going. I'm worried everyone is looking a bit shell-shocked, but
No, that's good.
okay.
Yeah.
Okay. At least you can go back and look at Persa and make sense of it. Ask me in person. Okay. So there's another really useful concept, which I call it a maxometry. That's combining the words maximal from maximally mixed state, sorry, from maximally entangled state, and isometric, or coisometric. And I won't explain exactly why that's the right word. I explain it in the book. But you can take some operator tensor like this that has that's homogeneous, okay, and I want to identify the G and the H as ancilla. So the idea that certain systems are ancillary is essential for the definition of what I mean by maxometry. Okay. And then the definition for this thing to be a maxometry, which means that this is a maxometric operator, is that these two conditions are true. Okay. So I always join the ancillary systems to the mirror, and then I leave, in one expression, I leave the incoming system open, and in the other expression, I leave the outgoing system open. Okay. So maxometric operators are pseudo-physical. What I mean by that is, if I ignore the ancilla, then I get an operator which is physical. So here's an operator and say, what's the notation I used? C, D, G, H. If I ignore this and also this, and if this is a pseudo-physical operator, then if you ignore the ancilla, then the thing you have left over after doing that is in fact physical. Okay. And so maxometry is the property you have there when this is also homogeneous. So there's no wires, there's no label wires joining the mirror in here. Okay, so it's just a definition, really. And you can show that unitaries are maxometries. Okay, if you have a unitary in there, it is just a maxometry. Here I'm using a property that if this is unitary, then we can just use the unitarity property inside here to get this. And then this is just a wire that attaches to the mirror, top and bottom. And you can show that that always just gives 1, which makes sense because you just get an ignore preparation followed by an ignore operator. Okay. And the converse, the inverse of that is also true. You flip that diagram upside down. However, not all natural maxometries. Here I'm talking about natural maxometries because they have these mirrors with the curly thing on. Not all these natural maxometries are in fact unitaries, and you can cook up examples that prove that. Okay. So then to finish, I'll talk about the Stein-Spring dilation, which is central to quantum theory. The standard Stein-Spring dilation we have in time-forward quantum theory looks like this. You have some operator, and you can represent that by a unitary, where you introduce an ancillary system, and then also you trace out over an ancillary. So any map in the standard time-forward presentation of quantum theory can be written like that.
What did the bar mean? I forgot.
Remember the bar, I used it before to represent when you're in the time-forward picture?
Okay.
Yeah, so that's what it is. And you can also include outcomes. So it was realized, not much time later. Well, I think this elsewhere, that you can represent outcomes. So here's a operator in the time-forward theory that has an outcome. And I can write it down like this. I basically just do a measurement in some basis afterwards. Otherwise, it's essentially the same. And now I represented that preparation of the ancilla like this, just to sort of connect with the notation I was using before. And so you would think, well, in the time-symmetric theory, you would like this to be the dilation. Okay, this looks time-symmetric. It kind of connects with the thing. And it might be true that this is the correct form. It might be that you can always do this. However, I haven't proven that. What I've proven instead is that you have a maxometry in the place of that unitary transformation. So the theorem is that any operator which is deterministic and physical, any operator is deterministic and physical if and only if we can write it in this dilated form where we have a maxometric operator there in the center. Okay. And there's a few things to say about that. This is the last slide. The dilation I showed you with the maxometry isn't unique. So you can find, there exists a dilation with some maxometry, then you can write it in a different way. And that there are some examples where you have a dilation for maxometry, but you can find a way to rewrite that same dilation using a unitary in the center. So that motivates this definition that we say an operator that can be given a dilation with a unitary, we call it constructible. And the reason for that is if it has a unitary in the middle, then each of those objects that make up the dilation is physical, and you could imagine doing it in the laboratory. Whereas if some of the elements are not physical, then it doesn't provide a prescription for implementing that operator in the laboratory.
What are the conditions that maxometry that is not physical fail to obey? Like it's just
I can write down examples. Yeah, I think I can show you some examples. And it just doesn't. It still obeys the positivity, but it doesn't satisfy forward and backward causality in general, because you have to trace over. You always have to trace over both ancilla on the top and the bottom.
But then
To make it physical. Whereas physicality says that this thing should be physical without tracing over the bottom. So.
But then, if I have an operator B which is time symmetric,
Yeah.
and then I consider a dilation of it,
Mm-hmm.
and I take the time reversal, it's not. I mean, okay. So after you ignore the ancillas, you'd still satisfy
Yeah.
backward and forward causality because it's just the same as the operator which is time symmetric.
Yeah.
But if you don't trace the ancillas first,
Then it might not
then you
be.
might not. Okay.
Yeah.
Mm.
Yeah. So that's the definition. Yeah. So you could conjecture that unconstructible operators exist. You can conjecture that that there might be operators that can't be written with a unitary. And I don't really know. I have some examples on either side, and I haven't really proven. You could also conjecture that all operators are constructible. I don't really have the answer to that question. Now, in standard time-forward quantum theory, the Steinspring dilation allows for peaceful coexistence between the church of the larger Hilbert space and the church of the smaller Hilbert space. Because in the church of the larger Hilbert space, you say, well, I just have a unitary acting on some pure state, and I can always recover that picture using the Steinspring dilation. So these two churches can get along, even though they have fundamentally different beliefs. But if you go to this time symmetric picture, and if that conjecture here is true, then we have holy war. And,
Exist, you mean like unconstructible operators exist? You mean that they sometimes happen in nature?
yeah, so there are physical operators that cannot be written down in this dilation using a unitary. Yeah.
Have you proven that this exists, or
No, I haven't, because so the theorem, let me just go back to the theorem here, is that you can always do this. In fact, an operator is physical, is deterministic physical if and only if I can write it in this form. But that doesn't mean that I can't always find some way of writing it where that's a U. So the uniqueness part of the theorem is missing. And it's interesting to look at the examples, they're in the book, where you have something that has a non-physical maxometry, but then suddenly you can move things around and suddenly it has a unitary there. Those examples are kind of weird. Yeah. Okay.
So would you say that in this time symmetric theory, the church of the larger Hilbert space would put an additional restriction on what it means to be physical, namely that you have a unitary dilation?
Yeah.
The smaller Hilbert space would only make the
Yeah.
physicality conditions that you've already been talking about.
Yeah, I think that's right. And then I think, so I would be cheering for the smaller Hilbert space church in that case, because the fewer conditions you have, the better. Yeah.
And I wonder, why you call ones that have a unitary dilation. Why do you call them constructible? Because that already.
So if this was a unitary,
Yeah.
everything else in here I can prepare in the laboratory. So I can make this thing. This thing is physical. There's maximal. There's maximal preparations. There's maximal results. They're physical. The ignores are physical. If this is unitary, that's also physical. I can prepare it. So then I can prepare it in the laboratory. But if it's not physical, then I can't construct my operator in a laboratory by following the prescription that's given in this picture.
But if we're in just a smaller Hilbert space, why would we care about wanting to represent it in something like the right-hand side in the first place? Can't we just say that B hat itself is physical? So
Yeah, I think that's right. I mean, the only reason you would care about this is to prove some theorems. In the second half of the book, when it comes to these complex operators, you also have a dilation, but then you can go a bit further and consider operators that correspond to different causal structures. And so then you have dilations that sort of mirror that causal structure. So there's a whole bunch of theorems you can prove there. And they're mathematical theorems, but they don't have the constructible physical interpretation. Yeah, so maybe it just opens more questions without, it doesn't really resolve those questions, what the physical interpretation is of that. But at least it provides a mathematical way of dilating more general causal objects.
okay, but so what if there's a B hat that is physical yet non-constructible?
Yeah.
Would you really say that there's no way to implement that in a lab, but maybe it can still happen in nature out there in an uncontrollable way?
No, I think you can still implement it in the laboratory. You just can't implement it in terms of these more basic objects. Yeah. Yeah, I mean, which I think is fine. I mean, why do we like the Stein-Spring dilation in standard quantum theory? And one of the reasons is because it provides a way of implementing them, or thinking about how you would implement it in a larger Hilbert space. But I think also it's just mathematically interesting that you can break it up into these different parts. And so I think the mathematical interest passes over. The physical interest is under pressure.
No.
Okay, I will, after declaring holy war, I will stop.